I'm not used to this, but I'll give it a try here. So, truth in advertising, I don't know how much model validation selection you'll get out of this, but you'll get something. So, again, I'm Greg Lawson. I work at the Energy Information Administration, which is our arm of the Department of Energy. And this is a presentation that I gave it recently in the summer in Denver at the Joint Statistical Meetings, JSM. I was encouraged to repackage it and submit it here. So I'm going to outline a recent electricity initiative here. Talk a little bit about what that is to give you a flavor of why you might care. Go over some of the necessary background for electricity markets, in which you'll hear about RTOs, or regional transmission organizations, ISOs, independent system operators, and locational marginal prices, LMPs. Get to what those are. Talk a little bit about the project so far, its progress and hurdles, and I'll end with an example of future analysis possibilities. So that's between all of us, you have to submit abstracts well in advance of conferences, and you don't always deliver on results. So it ends up being a little bit more like marketing than anything, but still stand by it. So here we go. The electricity, so EIA background, it's Federal Statistical Agency, or DOE, independent and policy neutral by charter. There's only one political appointee at the top, our administrator, of over 300 employees. So known for world-class energy statistics, primarily from surveys. We also do, interestingly, projections, official projections for Congress forward under assumed policy scenarios. We produce a principal economic indicator, our weekly natural gas storage report, which is market moving and treated with secrecy and respect upon its preparations. So you probably already know all that, but in case you don't, just needed to say that. Our administrator, Linda Kapawanu, has announced an electricity initiative as one of her key priorities. So EIA has pretty strong data offerings that exist in electricity. They have traditionally they have always been aimed at the state level and at the nation. And we want to expand these coverings, we want to expand these offerings by covering these wholesale electricity markets. Again, I'll get into that, but these are the engines by which supply and demand are set. Which they meet, and they set local prices for electricity. And the wholesale prices, they're different than the retail prices you pay to Pepco or whomever. And about 2/3 of the US have these structured, coordinated wholesale electricity markets. You'll hear them either called ISOs or RTOs. They've been set up under the federal FERC, so Federal Energy Regulatory Commission. And it's all about ensuring open access to the transmission system. So there's a map here, United States and also Canada. So in the United States, there are 7 organized markets, RTOs and ISOs. Part of the agreement that they enter into upon forming an ISO or RTO is that they have to make a certain amount of data public. In fact, there's troves of data that they make publicly available through their own websites and FTP sites and APIs and the like. Instead of creating a new survey, that would be EIA's go-to move. Instead of doing that, we proposed in this case, this electricity initiative, in our effort to go out and gather, or to have an offering for customers at EIA.gov, we're going to collect the publicly available data. And so the value proposition here was that we wanted to co-locate and demystify this data. So co-location, so there's 7 different ISOs, RTOs out there, which effectively means that you have 7 different data providers, and each one has its own formatting and conventions and definitions on things. You almost get the sense from some of them that they're don't want to necessarily make this easy to get. So there's a certain amount of there's more than you'd expect data wrangling involved in trying to get some useful formats for people. And subtly, because of all the differences in conventions and definitions, not so much in data formatting, but not all the data here are quite apples to apples. Some markets have price caps that they put in and different procedures towards price formation that go in and different rules. And it means that if you take a price from one market and just put it next to another one, they're not necessarily the same thing. And so there is an opportunity for EIA to house the most salient public information, one location in EIA. This will increase the ease of access. So we have, it is difficult. Some people have hour beginning, some people have hour ending, some people have, some providers have different time resolution for their data series. So we can put them all in essentially one place. And then, I don't know how to say this next day. So I'm saying it's provide a curated data offering. So this is this data. There's a huge number of people who are financial markets that trade on wholesale electricity. There is a great volume. Perhaps I don't even know what the appropriate number is, but in short-term markets for power delivery the next day, maybe, I don't know. I don't want to be quoted on it, but I'll say more than half of the market volume is probably on people just trading financially. There's a lot of people who want this information immediately, and there's a lot of detail that you get out there. Those are not the stakeholders that we have in mind. We have to get a curated data offering of the largest hubs, the largest sort of interfaces and zones in these markets that give people that are in less sensitive positions. Maybe you want to make a decision, maybe you want to get educated, maybe you want to do some basic research on this stuff. That's the sort of stakeholder we're going after, and we're going to be able to get the publicly available data, the ones that we think are going to complement the rest of the data that EIA has. And then in that environment, it'll be naturally interleaved educational material and explainers. This is something that we do quite well, I believe. And there's other electricity data, complementary data sets that it'll be in the, will be housed alongside of, and one can make easy connections for future. So, okay, here's an example. This is going to be the first thing we go after, something called locational marginal prices, which you may not be familiar with, so I'm just going to step forward very quickly. So wholesale prices are cited as LMPs, and they are prices. So the P part of LMP is, they're US dollars per megawatt, and this is for power purchase for delivery at a certain place. Now they're called marginal in the sense that it's an intersection of supply and demand, which sets the price of power. So some central, non-participatory, neutral third person or party is at the center of these ISOs, and they are taking in supply offers, so generating units out there in the landscape. So our local market in the DC area here would be the PJM. And so PJM is taking in generating unit offers for everyone in the market of how much power they would be willing to generate at what price. And this is typically done at a day-ahead time scale. So you might have power, natural gas plants, whomever else, nuclear plants saying, I think we can achieve this at this price. And then you have demand bids. So you have consumers, and not necessarily you at your own house, but your utility. So Pepco says, hey, we have a sense that it's going to be a hot day tomorrow, and we're going to need to cover this much power for all the air conditioning use we're anticipating. Or you might have some big industrial consumers who, they, maybe not in this area, but maybe they want to make aluminum, some highly energy intensive process, and they say, this is how much power we expect to need tomorrow. And they might actually have price points at which their demand might change. So a lot of people don't think air conditioning is very elastic, but if you were making aluminum, you might be willing to hold off that night if power got too expensive, something like that. So you could have these supply offers and demand bids, and then the central party will essentially stack up all the supply offers from cheapest to most expensive, match it with the intersection of demand bids, and come up with a marginal unit. So whatever power plant that was at the center, at that intersection becomes a marginal unit. That then sets the price for electricity for that hour. Everybody gets paid that. Even if you bid in at zero because you're a wind farmer or something like that, you still get paid your $40 a megawatt hour, depending on who the marginal unit was. Now, the reason that we call them locational is that prices can vary geographically based on the network topology. So suppliers and consumers aren't necessarily next to each other. You might go through this open access network of power lines, and you can get congestion, so i.e. traffic. Any power line only has a certain capacity of megawatts that it can carry. Also, if you have to carry electricity farther distance, you're going to incur further electrical losses in the process. And so these processes, particularly of congestion, but also of losses, affect the ability to deliver power, and the local wholesale price of power where you get it delivered will reflect how difficult it was to get power to there. Hope that made sense. So this is LMPs is the first thing we're going to go after in this electricity initiative, this RTO portal. We kind of call it in-house, not an official name yet. We want to collect all these from different providers. This is not in the original JSM thing, but I thought maybe the technical approach would be interesting to people here. We've been made as a team to kind of go through some hoops as we're adhering to the architecture for this approach that will be implemented for everybody in the near future. And as I said, we're going through it first. So on the left, to the left of that vertical dotted line there's the outside world. So on the top left, we have the data providers, represented by some clouds there. And we at EIA are instituting a so-called DMZ, a demilitarized zone server, which is something that can legally sit outside of our firewalls and communicate with the outside world. And so we're going to capture data, do some scans on it, make sure it's okay to bring into our internal networks, and then we'll bring them in, validate that we actually got what we thought we were going to get, put it in the database, eventually get it out, publish it to the customers. So we're implementing, because this new DMZ server sits separately from the rest of EIA's internal servers. If we wanted to do things in our lingua franca, which up to now has been something like SaaS, we'd have to get yet a new SaaS license, and they're not interested in the expenses incurred there. And so there are these nice free and nimble resources that pretty much everybody who's at GASP, I'm guessing, is interested in and using. So we've looked to Python to use scripts to pull data providers and access APIs, download raw files. So we are now, a new mode for EIA is we're creating these Python scripts to go out and do this work. And I'll get to, we have several modes we have to run in. Then once we get them and we capture the data and it's scanned and approved by IT to bring in-house, then we're going to then follow up with either more Python or potentially SAS, but we're leaning towards Python to then parse and validate the data, wrangle it into storage form. And so we've been told, you got to validate the data that comes in-house. It may pass a virus scan, but it may be some weird code as opposed to the data you're expecting. You bring it in and try to put it in the database, it might get executed and do bad things. Right? So a lot of emphasis here on security in this. And then it eventually gets packaged into what EIA.gov wants to show, published, and then plugged out again to the outside world in the bottom left corner. So our progress has been forward. We've run into some hurdles in that scraping public data is a different mode than what we typically do. We have in mind robust operational code. We are the coders ourselves, like analysts in the electricity office. We're not saying, hey, IT department, do this. We're not getting contracts to do this. It gives us a little bit more nimble positioning to when data providers change their formatting or whatever, we can catch those and get them put back up immediately. We're going to have to run an operational mode to keep things up to date. Again, we're not going after financial traders. We don't need to be up to the second or millisecond. We just need to keep it relevant so that if you go to EIA.gov on a certain day, you'll see the data that was relevant for hopefully that day. We also need a historical mode to backfill archives. And so this technical stuff is the domain of me and my co-author here, April Lee, who's in the audience, and our team. And we're dealing with that. But when you go in, peel this onion, you get things you don't expect. So you bring in the lawyers. We need republishing rights. So this is all publicly available data, but everyone comes with more than just the boiler print stamp. It says boilerplate stamp that says you can't republish this data. You need rights to, and we believe that we will be able to get all those because after all, if not, we'd have to administer a survey, which federally they'd have to probably abide by. But it still takes time to work those out. Thank you. Front end display, we have high standards for our website, and we're going to have to work with the Office of Communications to get this approval to go out to the public. And there's a whole bunch of things that we want to put together eventually, but as I said, our minimum viable product is going to start with these prices that I've described. So in the interest of time, I'll just go ahead. There's an example that I wanted to put forward. So you might have heard that the state of Texas has a lot of wind power. It's very plentiful. Generation, however, is often very far from the load centers being where people demand the power. So there's a map that I got from EIA.gov that shows the location of all the wind plants in Texas and nearby states. And you can generate a lot of power up there, but people down in Dallas and Austin and Houston are the ones that really want to use it. And sometimes the lines that connect all the wind plants to where people need it can get congested. And this can lead to so-called to negative power prices. So from an economic point of view, like they're generating too much power and things are congested, it's kept in an island. We can't get rid of this, please, we'll pay you to take our power. It's in their interest because they get tax credits for generating power, so they'll take a negative power price if they have to. And it'll also raise the price of power in Houston. This is that locational aspect I was talking about. So in the interest of time, I was going to go through a little scenario here, talking about the balance of supply and demand and expectations. So maybe I'll walk through quickly. There's a lot on this chart. Okay, I'll go quickly. So this summer, in June 7th, there was this spike in power prices that happened in the afternoon, and prices went up to over $600 a megawatt hour, which seems like a lot. You can see in the top chart there, the brown line, in most hours, it's down pretty low. The price of power is, I don't know, $30, something like that, 35 in the summer. So 600 is a lot. Hey, what happened? It didn't happen on the Saturday, the next day, the 8th. And so you can start, if you had all the data housed together, in the middle swath that you see here, the gray shading shows you what the peak hours of the day are. And that's when that sinusoidal kind of block-like curve peaks in the afternoon. That's when peak demand happens. So when it's hottest and people are using it. And it seems like the peak demand on Friday was about the same on Saturday, but prices flared up on Friday. So what was the difference? Well, down at the bottom in that same center chart, you can see a light blue and a dark blue line. This is the expected amount of wind power that they were going to get versus what actually occurred. So it's actually a forecast here. That light blue is what they thought they were going to get from the day ahead point of view. The blue line, the dark blue line, is what they actually got. Wind power is plentiful in Texas, so this is very low values to have it so low. So typically, you can see it started to rise up by the end of Saturday, and you see much higher values than that on other days. So to have it so low, but the real thing that seemed to happen is, in the bottom is the difference between what was projected and what they actually occurred. And you can see that there was a big mismatch at the beginning of that shaded area. So they thought they were only going to get about 2 gigawatts of wind. They ended up with 1, and that led people to scurry off in a hurry to figure out how can we cover this gap, and it led to turning on presumably other more expensive sources of energy that can react quickly. Anyway, this is like an anecdote really, or a case study that you could easily pull together within one environment once this electricity initiative has been further fleshed out and released to the public. There's many other, like the California duck curve and responses to the polar vortex and the like. And I'm sorry we can't do it today, but this is where we're heading. And that's it. We just summarize. It's a key piece of electricity data from the point of view of GASP. We're having to back into this new data collection mode using these scripts to collect things in Python. And I think it'll be better. I don't know. In there. Thanks.
Does anyone have any questions? We've got a couple minutes. We can take a couple questions. Oh, okay. Great.
I just had a question about the map that you put how it's generated. So why is it just
This one?
There's such a big gap down there where like all the air, is it because the points just not
So it is the case that meteorologically, there are some places same way that there is for solar. There are some places that happen to, well, actually not true. It's much more varied for wind, and there are just some preferred wind belts. The windiest places of heat are places that cannot. But when being on a high elevation ridge, has out there make settlements because it's windy and there's not very good access to water or whatever. So there's lower population out here in these plains and panhandle areas. Really good. Yeah. You could probably put a wind farm there, but it wouldn't be as valuable.
Great, that was really interesting. Anything from the? Okay, great.
I think we'll be okay. Down here at the bottom.
Yeah. Great. This is.
What options are here? I didn't study them. If we click this, and then
Shares in the middle. Yeah. And yeah. All right.
look that one.
Yeah. Thank you. Let's see if we can go back a little bit though.
Yes. There you go. Great. Take care. So our next speaker is Joel Hutchinson from Tableau, and he's going to speak on Tableau for data science. Thank you.
All right, everybody. Thank you for having me today. So let's get into Tableau for data scientists. Again, my name is Joel Hutchinson. I am from Tableau. I don't know how many of you guys have worked with Tableau. It's a data visualization platform. And I'm going to be talking today about how we can use that platform in conjunction with a lot of the tools you're familiar with. So whether it be R, Python, how can you plug in those technologies and use them directly inside Tableau? All right, so let's understand the why. Why do we care about Python, R, and Tableau? When I tried to first answer this question, I went out to the internet and I found on LinkedIn the top skills that are required by data scientists. And if you look at the top 10, the top 2 of them are Python and R. I think in recent times, Python has taken the lead there. But I was curious what other skills were on this list. And as I looked through it, you find that Tableau is actually there at number 8. So it's the only data visualization platform that's listed in the top 10 skills out there on LinkedIn for data scientists. I thought that was interesting. You see other things out there like SQL, Jupyter notebooks, Linux, Shell, but Tableau, again, is the only data visualization software. Further in the article that I was reading in Forbes, it said that storytelling is an essential skill to have for data scientists. It's not enough to draw out those insights and understand your own data that exists in your project. You need to explain that to novice people. Take that knowledge and share with others who may not be into the underlying nuances of your data. So storytelling being that critical skill, that's where Tableau comes in. Tableau's mission is to help people see and understand their data. To simplify that down, we help people tell their data story. Take your data that you have, create dashboards, share those dashboards, and let other people understand the same insights that you were able to draw out. So a little bit more on telling your story. So on the left-hand side there we have our advanced analytical languages. So these are, in the case we're talking about today, Python and R. The benefits there are they're peer-reviewed mathematical and statistical packages. You can help enrich your data with machine learning and natural language processing. You can offload that heavy lifting of or heavy statistical testing onto these programming languages. And they also help with creating and iterating through your regression models. Now on the right-hand side, you have Tableau, and the benefits there are it's very easy to identify visual patterns, relationships, and trends. So we we have a software package that allows you to basically draw out those insights visually, which is what our brains are more inclined to do rather than just looking at rows and columns of numbers. It also allows you to easily share and communicate those insights with a broader audience. And then finally, at the bottom there, Tableau enables novice people to pick up your work if you're a statistician and maybe ask and answer their own questions in a very user-friendly environment. So the combined benefits together, it's really being able to turn your data over to broader audiences. So it's not just having a spreadsheet that you and only you get to see. It's allowing a large, wide group of people to see the data and understand what's going on in there. You are able to uncover more insights. It enhances, having R and Python inside of Tableau actually enhances the out of the box capabilities. We do have our own statistical functions inside of Tableau, but often people want to go beyond that. So maybe it's not the right algorithm. You want a different algorithm. By bringing R and Python into the mix, you're able to get those extra pieces of functionality. And then finally, it helps you to easily tell that data story. Let's get into understanding the how. How does all this work? So we start off with Tableau Desktop, and that's Tableau's flagship product where you would start to build your insights, your dashboards, and your visualizations. Obviously, you need data, so you're going to connect to data, and you can connect in one of two fashions. You can either connect to an extract or live data and pull that data back into Tableau Desktop. From there, you're going to create what we call a workbook. And this is just, you can think of a workbook as a collection of visualizations or dashboards that you create. And then you have the ability to publish those workbooks up to what we call Tableau Server. And Tableau Server is a platform for sharing that out with a wider audience. So you could do all of your work in desktop, but when you want to get to the point where you want to share that content with a wider audience, Tableau Server is the platform for that. And then Tableau and Server in turn can connect those same data sources either through an extract or a live connection. So if we take a look inside these workbooks, there's actually what we call a script function. And this is where you are able to bring in R and Python. It's a special kind of function. It takes input data and sends it out to external services. And we have one for Python called TabPy and one for R called rserv. In turn, these two different services will pass the underlying code that we care about and data that we care about to the underlying R code or Python code, crunch the numbers, and then send that back into Tableau. So we're actually offloading the R and Python into an external process, but bringing the results back into Tableau. There's the result data coming back in. Now, the other approach to this in the Tableau framework is to pre-process the data. So you can run your pre-processing in R or Python ahead of time, and then automatically create what we call extracts in what we call a hyper file. These extracts are proprietary data storage for Tableau that are optimized to run in Tableau. We have an API, as you can see here, called the Hyper Extract API, which will allow you to create those. So in a single script, you could run your R or your Python, as well as the creation of the hyper script. I heard about, talked about this morning about the need to data wrangle. We also have another tool called Tableau Prep, which allows you to clean up your data and also run these scripts directly in kind of like a lightweight ETL environment as well. So if you do want to clean up your data before it even moves into visualization, there's quite a few different alternatives there. So just to talk a little bit about the two external services, first up on the top there we see TabPy. It's simply going to allow for that remote execution of the Python code outside of Tableau. And then below that is rserv, and rserv is a TCP/IP server, which allows you to execute and initialize that R code outside of the Tableau environment. The difference between the two is TabPy was created as a product by Tableau. You can kind of see that in the name TabPy. rserv was community created, and we don't have any affiliation with that. But I did provide links in this. I think we'll probably give out the slides at the end, so you can take a look at both of these after the fact. So let's look at those script functions in Tableau and see what they actually look like. So this, on the left-hand side, we have one that we're working with here for outliers. The script functions come in 4 different formats, so script, real, int, string, and Boolean. And it really just depends on the type of data you're getting back on which one of these ones you would choose. So first off, you would determine which one you're going to use, and then obviously add that into the function on the left. And then you're going to give it the actual R or Python code in that second section there. So the larger box there, we see the actual code that's going to be executed in either tabpy or rserve. Now at this point, Tableau doesn't process that large string or block of code at all. It simply treats it as a string. The next part here is part 3 at the very, very bottom you see there. And this is the data that we're passing from Tableau out into the R or the Python code. It can be fields, it can be parameters that the end users interact with, but all the fields that we're passing out they have to be aggregated in some format. So min, max, average, etc. And then finally, where we're stage 4 here is where we're actually mapping those Tableau values, the data that's leaving Tableau, to the arguments that are in the Python or in the R code. So you see them listed as arguments there. All right, if we get into the nuts and bolts a little bit, I do have instructions in here on how to install tabpy and rserve. I would say the installation of these 2 different technologies shouldn't take you more than 15 minutes. So it's not a huge lift to get these up and running. I actually have it running on my laptop. So they do run on smaller machines as well. I was going to show you guys a demo today, but this is not my laptop. This is the room's laptop. So maybe after the break, if you guys are interested in actually seeing some of these models in desktop, Tableau desktop, we can do that. All right, there's rserve. And then finally, from within Tableau desktop, you simply would provide the server name and port for either rserve or tabpy that you're going to connect to. This is just taking a look at what that interface would look like. So that's how you would connect desktop, and this is just a diagram of how you might connect Tableau server. So Tableau server also would need to know about your rserve or your tabpy. You need to simply specify the server name and ports, so Tableau server can connect to these 2 technologies as well. Some additional considerations here. First off, Tableau unfortunately only allows you to work with 1 external service. So what that means is if you have an environment that you have both R and Python, your Tableau server can only communicate to 1. Huge gaping hole in our technology. The developers know about it, so they are trying to address that so you can have connections to both. The next one there is if you do work with Tableau Online or Tableau Public, these external services are not supported there. So Tableau Public is actually a free version of Tableau Server where anybody in the world can actually share their visualizations. Quite a few of the folks, in the government who create visualizations, they'll post up visualizations to Tableau Public that can be shared with a larger audience there. Security best practices would indicate would suggest that you should run tabpy or rserve on a separate machine from your Tableau server. And the reason being there is Tableau server eats up your memory. You don't want to have any kind of conflicts with the underlying code that's running. If there is latency, the 4th and final point here is to consider that pre-processing approach that we talked about, either running your Python or R scripts ahead of time in Tableau Prep Builder, and then building out with the extract API your hyper extract. Let's take a look at some use cases now. So first off, we have forecasting time series data. This is what it would look like, the 2 different visualizations. So this is being visualized by Tableau, and in both cases, we're using forecasting models. On the left-hand side, you can see we've forecasted it with Python. On the right, we've done the forecasting with R. I was surprised to see how close the 2 different languages came as far as the appearance there. So that was, I mean, it's a good thing. That's what you would expect. But so here's the underlying code for each one of these. So we are using the script real function. On the left-hand side there, for R, we're using the library forecast. On the right-hand side, we're using NumPy, pandas, and exponential smoothing, as well as stats model. And then you can see both cases we're passing out at the very bottom, we're passing out the average temperature and the average forecast week. So this would be what you would create in Tableau. You could push a lot of this code out into the underlying models, and that's one of the benefits here. I hear a lot of people who are working with R or Python, what they'll do is they'll tweak those underlying models that these scripts are referencing, and then they're able to quickly see the results through a visualization, and they can spot check it and say, okay, that looks better, tweak it again, Once you've created your dashboards with these scripts, you don't have to touch the dashboard again. You can switch the models without interfering with your dashboards. Here's another example. Our company is based in Seattle, so we love examples of Seattle. This one is clustering crime. On the right-hand side, we're using R. On the left-hand side, Python. But what I like about this example here is that the end user can actually work with this dashboard and switch the parameters. So I want to look within a 200-mile radius, for instance. I want to look for only robberies. All of that will be pushed back into the models and allow it to then cluster based on the selections that the end user has made. So it allows your end user, like somebody like me who may not understand what these models are doing, I can still interact and I understand what this dashboard is telling me. And then there's the underlying script code for each one of these. In this case, we're using the script string function. All right, this is where I was going to give you a demo, but please meet me outside afterwards, after everybody's done talking for the first session, and I can show you guys anything you want to see as far as these different examples. All right, thank you.
Do you have any questions? Great.
Thank you for letting me ask my question. So I see that we can actually run our in the Tableau environment and then send it over to Python servers. Right? So my question is, if your code have any bugs, how do you debug them using that interface, where you just send that string into the Python? And if you have any debugging functionality, you have to manage it.
For the debugging, my experience is when you start more you do have a console, you can actually see the error messages appearing there. So I definitely use it for my console to look at what errors are occurring.
Could you repeat that so that?
Yeah. So if anybody missed that on the call, the question was about how would you debug this. Both of these Tableau and RServe have a console, and within the console you can see the code being executed as well as any error messages that are occurring. So that would be the place to start debugging. Any other questions? Yeah, over here.
In your example with the crime clustering, how did you import them mapping?
The question, great question about how we got the maps that were built into the crime clustering. Tableau does come with free mapping. If you have desktop, you can use mapping service. We used to do OpenStreets. We switched over to Mapbox as a mapping server. But Mapbox is also a piece of mapping. There's another question back there. Just bring the microphone here.
What would be a good example of when you would want to just do it natively in Tableau and not rely on the external service? Like I would imagine Python, there's like a Fourier transform that you just can't pull off in Tableau quickly or whatever. The dragging and dropping on the interface is too cumbersome. But when would be an example where it's just better to just keep it all in Tableau?
So great question. One of the examples I was going to show was clustering that Tableau can natively do. I had a side-by-side comparison of Tableau's clustering, which uses one algorithm, and then using a different one in Python to get better results. So in some cases, based on the algorithm, you might want to switch from using native Tableau analytics to what you can get in R and Python. Does that make sense? Any other questions right here? Yeah.
So from someone who does not know that much about Tableau, what advantages does it have over R and Python's like native visualization like that?
Sure. So as far as advantages over the visualization in these other products, Tableau's bread and butter is visualization. They've been around for 15 years. That's what they've specialized in. They've made incremental improvements. They've also created a framework that's easy for the novice to pick up, but then has the capabilities for
further down, might go to Python expert, and still be able to use that tool to easily and quickly create those visualizations. So having worked at Tableau 3.5 years now, I'd say time to insight. So I can easily, much faster, create a visualization that is interactive, accomplishes my goals faster than I could. Any other questions? All right, thank you guys.
Daryl, nice to meet you. I'm sorry. Thank you. You guys are going. I would just like to fix something. I'm sorry. Go ahead, you can introduce him.
Right, okay, we'll follow with our next with Daryl. Real from RTI.
I don't know why it's showing. Not showing.
Click, can you run the slideshow or run the presentation and then click share that?
That's what I thought I was doing, but oh, I hate this on.
It is actually movable if you
Okay.
Okay. Okay. Well, here's Daryl.
Well,
Okay.
yeah, we don't know what's going on.
Okay, so we're going to talk a little bit about statistical learning for complex survey data. And the particular example I'm going to use is using cross-validation for variable selection and generalized linear models when you have complex survey data. So there are a couple books out there. Introduction to Statistical Learning, which is written after the elements of statistical learning. It talks about statistical learning and model development and things like that. You could also think of it of machine learning or something similar. And the issue is that these books are good, but they don't talk about complex survey data. And so I went and looked and tried to find some stuff, and you can find the occasional article about it. Like there's a recent article about using Lasso with complex survey data, but not a lot of these other techniques. And so I'm basing on presenting a cautionary tale for using these methods with complex survey data. So I do have an audience participation part. And the first part of it is how many people do some kind of modeling or machine learning or something like that in their everyday work? Just raise your hand. I'm just trying to get a feel for that. So that's almost everybody. And since this is about government collects a lot of data from big national surveys. How many people do that modeling with complex survey data? Okay, there's a few, not quite as many. All right, so let's get started. And so there are a lot of different ways you can, if you have a bunch of variables and you want to do some kind of variable selection, there are a lot of different ways to do that. They have these p-value based approaches where it's based on forward selection, backwards elimination, stepwise was just kind of a combination of those two things. And then there's a pretty common technique you see people use is by Hosmer-Lemershow in their book about applied logistic regression, where they screen a bunch of variables. If the variable has a p-value that's below a certain threshold, then they include that when they start their model development process. And then after they identify the main effects, then they'll look at interaction terms. That's used quite a bit. And then you have these ones that involve indirect estimation of the error, where you have AKI, if I pronounce that correctly, information criterion, or Bayesian information, or Mallow's CP. And then you have like direct estimates of the model error, and you can use that with a validation set or V-fold cross-validation, and that's the one I'm going to actually talk about today. And so just as a reminder, so here's an example for 5-fold cross-validation, where you randomly put the data into 5 groups. In the first iteration, you hold back the first group as the test group. You build your model on groups 2 through 4, and then you run your data that you had held out through the model that you had, and that's going to give you a predicted value. Now you have an observed value and a predicted value. You take the difference of that squared for squared error, and then you can do the second fold. So in the second fold, now you use groups 1, 3, 4, and 5 to build the model, and then you do the same process. You run the second fold through it, and you do that through all 5 folds. So at the end, you have a observed value and predicted value for every observation on your data set. You take the difference, like I said, of those two, you get to squared error, and you can figure out the mean square error. And the goal here is to find the model that has the lowest mean square error. And if you do a lot of machine learning, you have to get these tuning parameters that you have to use for various things. So if you think about it in that kind of context, the tuning parameter that we're going to use is the number of variables in the model. So I did a small little Monte Carlo simulation. I'm not going to go through all this in detail, but basically I generated a population. From that population, I drew 400 observations, and I created, what was it, seven variables that are standard normal on there. And if you look where I, so for the y variable, we know that we can use variables b1, x1, x2, and 3. But so we know that our real model only involves using variables x1 and 2 as legitimate predictors for the y variable. I mean, that's why we're doing a Monte Carlo simulation, because we know the truth and we can assess how our methods do with the truth. And then what I did after that, once I had the data, I used what's called informative sampling, and that means that the probability of being selected into the sample is related to the y variable that you have. And so you don't need to know the details of all that, but I did Poisson sampling, so I did a Bernoulli trial on each one to select people into the sample. Those are just some of the details. Okay, and so then what I did is if you look at the horizontal axis on here, we have in the Monte Carlo simulation, I think I just did 10 or 15 iterations to get it to make sure it was working. But this shows the cross-validated mean square error for every single model that we did. And it's trying to give you an idea of like, so the number of variables in the model, one, you know, that's all the one variable model. 2, the 2 variable model, 3, 4, 5, and 6. There's only one 6 variable model, so that's the variable we have. It has some of these things because on every observation in the Monte Carlo simulation. A little bit later on, we're going to sum all those up together. But this was just to give an idea to see what the error structure, the mean square errors kind of looked like. And so once we, okay, this is what it looks like for the, if we treated the data as a simple random sample. So we just ran it through like what most of your machine learning or methods for variable selection, they treat the data as a simple random sample. So that's what this is. And this is what the error kind of looks like for all across all the repetitions and everything in the Monte Carlo simulation. So then what we did we just averaged for each one variable model, we averaged whatever they were, depending on how many iterations we did in the Monte Carlo simulation. And so this is the cross-validation error. And the minimum one for a one variable model was 1.3385, and then 2, 3. And the reason 3 is in blue is because we know that's the truth. That's what we should really be finding. And then you go down to 4, 5, and 6, and you can see that this is a decreasing, the error is decreasing as we go down. So that means as we add more and more variables to the model, we're getting lower and lower mean square error. And actually, if we treat it as a simple random sample, the 6 variable model gives you the lowest mean square error. And we know that's not the truth because it should be giving you the 3 variable model. So now, I mean, there's only one 6 variable model, so we can find out what that is. And so it just shows here what the actual model is. And you can see them down in the blue is the 3 variable model, which we should have identified as the best model, but we didn't. And so now we're going to do that same thing, but now we're going to account for the complex survey design and the differential weighting. Well, we don't really have any survey design. We do have differential weighting because we did the informative sampling, so we kind of structured it that way. And so this is what the error structure looks like. And you can see now there's kind of looks like some gaps, white space in the top for the smaller number of variables in the model, 1, 2, 3. And then if we average over all these things, now we can see that the false validation mean square error for the lowest one variable model is 1.37. And then for the two variable models, it goes to 1.23 and then 1.087. And then when we get to the four variable model, you can see it just starts to add, it starts to go up a little bit. So the minimum here is the three variable model, but we still don't know exactly which three variable model. So when we do that, oh, it picks out a model that has X variables 1, 2, and 3, exactly the ones it should pick out because of the way we structured the Y variable. And then you can see it picks out these other models. So here's just a visualization of what it kind of looks like. So this is for the Poisson sampling, and this is where we're treating it as if we're accounting for the complex survey design differential weighting. So you can see that the minimum point here is you can see they go up a little bit, but they're going up. So there is a minimum there, and it's at 3. But if we did the same visualization for when it's a simple random sample, you can see once it drops down to 3, but then it kind of slightly goes down after that. So the reason this is kind of important, if you're building your pipeline and you put an automated procedure in there, even like this cross-validation, and you say, give me the model that has the average smallest mean square error after I've used cross-validation, in this case, you won't get the right model. It's going to give you the 6 variable model. But if you account for the statistical complex survey design differential weighting, well, here we only have differential weighting, but it will give you the best 3 variable model. What happens in practice is they have a rule called the 1 standard error rule. So when you're evaluating these red lines, you go to the lowest one on here, and here it has to be 6. And then what happens, you get a little confidence interval 1 standard error around that. And if you have a more parsimonious model that falls within 1 standard error, you're supposed to pick that. So if you didn't have automated process, but you built that 1 standard error into your pipeline when you're doing it, you can still identify curious with that model. But if you automate the process and you don't account for that, you would identify the incorrect model. And so I looked at a lot of things. I didn't cover them all here, but if you have weights and you do the cross-validation, how should you do the cross-validation when you break it up into those 5 groups? What I did is I randomly did the weights so that you had all kinds of weights in each fold. I actually sorted it so you had the smallest weights in the first fold, the second group of smallest weights in the second fold, and the highest weights in the 5th fold. That didn't really seem to matter. And then the example of the simple random samples, we're simply ignoring the weights. And then in what we treated as Poisson sampling, use the complex survey data modeling. We are treating the weights like they should be treated. We used the weighted mean square error when we calculated our mean square error, so you just have to make sure you do that. And the whole point of this thing is kind of emphasize that if you're dealing with complex survey data, which a lot of government agencies do, you just can't blindly apply these machine learnings or statistical learning methods without accounting for that, because you're going to get, this is just an example, and like in mathematics, if you say something true, you only have to find one counterexample to show that it's not true. This is the counterexample. It's a very simple one. We just had a weight. That was it. We didn't have a big complex survey with several stages of data collection, clustering because of that. We just had one weight that was informative, but still, this is the one counterexample that should make everybody a little bit nervous when they take their data and they put it into a machine learning thing without accounting for complex survey data. And the problem is those algorithms aren't out there yet. Like I say, I just saw an article not too long ago by, I think it came from a dissertation from I'm blanking on her name right now, but anyway, she was applying to LASSO to complex survey data. But there hadn't been a whole lot of research in this area yet. So I'm just asking you to be cautious. Okay, that's it. Thank you.
Thank you. Do you have any questions?
Thank you so much. Did you look at the sensitivity of someone who was 5 and said it to anything else? Can you get away with it? So you said it's default and you use 5. Yes. Did you look at the sensitivity of if you can get away with even fewer or anything like that? In the machine learning world, it's really expensive. Yeah. Yeah. So I only looked at because typically people do it. There are 3 common numbers people use, right? There's 5-fold, 10-fold, and then there's if you put every observation except you only pull 1 out, which is a right? I didn't look at other ones, but I can do that for because I'm building much more complex my calculations. I get this meeting, and so I can incorporate this one.
I'm going to try to do this. Yeah.
Any other questions? Okay, well, thank you for coming.
It's not working, is it? Well, it shows that I'm. I'm sorry. Let's see. See, I don't know why it's not. Let's just do it this way. I don't know how to get rid of this guy here. It's not. Okay, you just have to use this view. I'm sorry. Hopefully everybody can see it in the audience. All right, thank you.
Great. Yeah, so we're here today with John from GASP2session1B. He's going to talk about scalable non-linear integration in R with application of census and agriculture.
Oh, hi everyone. I was thankful to see this. I do have to mention this is the first time in my life I've ever presented with a mic. So I apologize if there's any choppiness. So as I mentioned, I work for the USDA Mass, and we are that kind of lucky to be in this presentation. We are going to talk about model development. And the point of this talk is just to show that it's very simple to even run fairly complicated models. So this disclaimer is required. Should I show? So first, I'm going to talk about our application for state, the census of agriculture. Then I'll go over the question that we want to answer, some of the challenges in implementing this question. And then I'll talk about the R implementation of the so it's already happened, okay. So I'll talk about the R implementations of these nonlinear logistic regressions, results, and then. Okay, so about the census of agriculture, it's conducted every 5 years and years ending in 2 and 7, using a list-based frame called the census mailing list, which we abbreviate CML. So it's a count of all U.S. agricultural operations. So that's the definition of a farm that we use right below there. So our only source of uniform comprehensive agricultural data for every county or the equivalent thereof in the US. So it is the leading source of information on US agriculture. So we get the census, and then from it we produce counts, and the question is, how are these numbers produced? So information from two sources is used. The first is the Census of Agriculture, COA. The second is a survey called the June Area Survey, which I'm going to abbreviate as GASP. So a little about the June Area Survey. It is area frame based. It is conducted annually by in-person interviews. So we take the survey by segmenting, sampling segments of land. And those sampled segments will be divided into tracts representing unique farms, basically. And what this does for the Census of Agriculture specifically is it measures any incompleteness in the mailing list. Because of course it's impossible that you would 100% certainty get everyone in the country captured by that mailing list. So this GAS helps us measure the incompleteness of that. So before going to the model, I want to mention a few assumptions that this model uses. So an individual's response to both the census and the GAS are independent, at least given information measured on those forms. And the probability of the response to the census is going to be a function of the variables measured on that form. So I'm going to do one more assumption just to make this presentation easier to get through. This assumption NASS does not actually make. But we're going to assume that farms and non-farms are perfectly distinguishable. While this is not true in the real analysis, it'll make this go faster. And of course, all the methods described here can also work. So just a little bit notation. So this script C is going to be the set of farms that ended up returning the census form, basically responding to the census. So we're going to call X, like normal, data for a given farm. And so little c is did the individual farm respond to the census? 1 is yes, 0 is no. So did the farm return the GAS form is little j. Also 1 is yes, 0 is no. So given all those assumptions, we can come up with this model, which is the number of farms is going to be the sum overall census responders of the inverse probability of response to the census. So you can tell that these probabilities are directly in the formula. So any estimation of them is very important to get a good estimation. That's the application, but the point is that the probabilities will be fit by logistic regression. So in words, the procedure is to just take the GAS and the census and collect all of the individuals that were on the GAS, as well as the individuals that were on the GAS that responded to the census. So using that data from the first step, we're going to model the probability of census response, which is a logistic regression. It's a binary outcome. They either responded to the census or they did not. And then we're going to use that model to now fit the probability of response for all the census records, and then we'll sum those inverses to get the final number. So what does this have to do with data science and model validation? So as I mentioned before, all the estimates produced by the census depend on the response probabilities. And currently NASS uses linear logistic regression to model these probabilities. So the question is, how realistic is that assumption of linearity, essentially linearity of the logic with respect to the variables? So we can at least get an idea by taking some nonlinear options and checking how they compare to the linear case. So what is our metric for doing this? Well, we're going to divide the match data into a training and validation set. We're going to measure the performance on the validation set. And in a future study, we'll look at the impact on the estimates themselves. So the match data set that we create to model these probabilities is a moderate size. It's about 40,000 observations and 55 variables. This can be still large enough to stress computational resources, especially for nonlinear models. The reason for this is the models need to be run many times for both cross-validation and choosing between different models. And so because of this, the algorithms have to run fairly quickly, preferably sublinear time complexity and linear or sublinear space complexity. So this right here is going to wipe out some nonlinear algorithms from consideration. Basically anything n squared complexity or above, because in that case, you typically have to store some kind of proximity matrix. Like if you're using a support vector machine, you would have to store and possibly do operations on the kernel matrix, which becomes completely problematic from a scalability perspective. So typically scalable algorithms use something called mini-batch stochastic gradient descent. So for that case, we just take a sample during each optimization iteration and calculate the derivative using the subsample. So that gives us an unbiased estimate of the true gradient, and then the complexity will be determined by the batch size. So as long as you take a small enough batch size, it should run fine. So some of the algorithms that we're going to look at that employ this mini batch method are, well, one is linear logistic regression. That's the default. We're also going to look at extreme gradient boosting, which in R is just the XGBoost package. And we're also going to look at a deep neural network. There are a couple of different options for this in R. We use ANN2 here. So in the next couple of slides, I'm going to give what the R implementations will look like. They're actually pretty simple. And I put some references at the end. So if you want more details to really dive into this, you can take a look at those. So I'm going to go quick on this one. I think a lot of people probably realize how to do a normal logistic regression. It's very simple using R. The blue is the actual R code. Obviously, the little arrows are not R code. This is just PowerPoint. So that's just the R code. So the point is, if we look back, the linear model is very simple, and actually the nonlinear ones, the point is it's not much worse than the linear one. So for gradient boosting, we can create a list of all the parameters of this algorithm. And once we have this list, the model looks very similar to the linear case. You still put in your training data, you put in your 1, 0 class labels, and then you put this list in this parameter here. So this trains the model. Now, if you want to look and see how the model performs on the validation data, you have to make a prediction on the validation data. So this is this step. So I just call it guess, hopefully a good educated guess. But we predict the model on X validate, which is just the validation data. And then the guess it outputs probabilities. So typically, if it's greater than 0.5, you say it's a 1, otherwise it's 0. So this is what this step does. And then we can get the accuracy by taking a look at the length of which the guess vector is equal to the true label, and then divide it by the length of the true label. So the other one we look at is the artificial neural network. And once again, you're going to have some model parameters. So this is just the training data. This is your label. So one thing you have to choose with the neural network is the number of hidden layers. Just to make it simple, in this example, there's only one hidden layer. But if you want to have more than one, you can just do a vector. So if you want 2 hidden layers with 10 units each, you can do C 10, 10. The loss type just tells it to do the logistic regression. Activation function is another parameter you can choose. Same with the optimization type. This one is kind of the most popular, so that's what I used. All these other, the learning rate is actually very important. If you just randomly run the neural network, your learning rate probably will not be correct. So you have to very carefully tune that guy. These two, though, are just defaults. You can most of the time leave unchanged. This guy is also very important. That's the number of times you have to pass through the training data. In this case, the data set was complicated enough that we needed to pass through it a lot to achieve convergence. That may or may not be the case depending on your problem. This is how big your batch size is, which is going to be dictated by your allowable memory. So once we have this, though, it's the same. You can still make a prediction, and then you can still check the accuracy of the prediction. So I just wanted, and this one is pretty big, so I'm not going to go over it super long, but this is an example of the full workflow. So basically, you have to get your data by whatever means possible. And then you're going to use your validation set and loop over parameters checking the accuracy. So here is the getting the data. In this case, I have the 40,000 is not that hard, so we can just read it from CSV. Obviously, like security issues, I cannot click the exact name of the file, but in general, that'll be your file name. So here we just create the training and the validation sets. And depending on your application, you may want to scale it. And the type of scaling is an additional parameter. Here I just use min-max scale. So then this is the important part. This is the parameter choice. For the XG boost, there's two big ones. There are other ones too if you have more time. Two big ones are the max step. So that's how deep your tree goes. And the other one is the learning rate. So we take these, and what this does is it just makes a table of errors for each cross-validation iteration. And then we pre-allocate the accuracy. And then all you got to do is basically put what I showed you in the first slide in a for loop. So it loops all those different parameter sets and then fills in the accuracy vector. And then you're basically done. So to choose your parameter, typically you want to take the one that maximizes the accuracy, and then you can record it. So that so in this case, it happened to be the first row. That's not always going to happen, just coincidence. And then that gives you the accuracy. By the way, just because of the presentation that came before me, mathematically, you can show that the rates condition out. In this case, so you don't have to worry too much about the fact that one of them is a mistake. I'm not going to go over that. It's a little complicated. So we checked all these four models. So we did linear with interaction terms, gradient boosting, and neural network. So it turns out that the gradient boosting does the best, but it's actually not that different from the linear, which is a good thing. So while the extreme gradient boosting does win by like 3 or so percentage points, the linear model is still close behind, which is actually a very good thing in a way, because that demonstrates or that lends additional credence to results that have been posted on the previous censuses that have used linear regression. Okay. So for some future work, I for the sake of presentation, I would try 3 nonlinear cases, but we would like to try more in the future. One example is kernel logistic regression, but approximated by random features, which helps with the scalability problem. Definitely try more census years. I believe we have 2007, 2012, and 2017 data available. 2012 was this year. And we want to compare the actual estimated totals. So like once again, for simplicity and due to security access of getting the data, I just used a validation set, but one might want to see how sensitive that N is to each different model. So here are all the references. If you want to learn more about the census, you can check out the first one. For the model that's used here, the second one. And for all of these methods, whether they be R packages or like papers on the methods, you can check out the username. So thank you very much. Hope Mike wasn't too bad.
All right, are you going to email out that last slide with the list of resources to follow up on the calls we're talking about?
I don't know if I can email it because I don't have all of you. Oh. I was gonna say, I don't know if I can email it because I don't have everyone's emails. If you are interested, maybe you can talk to me after. I don't know if the conference will email it. Oh, okay, great. So they're gonna publish it.
So you find that there was not a whole lot of difference across models. Is there any test that allows you to explicitly check if cross-validation measurement error is different across models? Is there any package that does that?
So if you would like, you can use the carrot package that will do it. I'm not entirely sure if all of the models that I use are included in that package. I just thought it was simpler to do it on my own. So, but yeah, I would first check out the carrot package, see if that has what CARET.
So I'm wondering what's the class balance of your 1 class and your 0 class, and have you considered using the F1 test score or ROC to optimize your models?
Yeah, that's a very good question. I think it was about 70-30. In terms of using those, that would be something that we would do. The best choice still, I think, is to add, like, what we really want to see is the sensitivity of the estimates in the end. Like I said, to get the estimates, you need the entire census data set, and there's some, like, it's the government. There's some security issues in getting it out of its place, in a sense. But yeah, so ideally you want to check as many metrics as possible. Like you said, AUC or F measure, or just the validation set, or most importantly, I would think the actual estimate.
Anyone else? Any, you hear anything from